So I've put together a talk about electron microscopes and cameras. I'm an expert on cameras. I'm not really an expert on electron microscopes, except as something you connect to a camera. But I made an attempt to do a broader introduction. I'm not sure the level of expertise of the people in the school, but let's just dive right in. I'm also going to end with a little bit of an introduction to uses of the cameras that my company makes outside of Cryo-EM. Relatively short. Liguo, if you want to make suggestions along the way as to the emphasis or focus, I would be happy to adjust as I go. All right, so basically a microscope is something you use to look at things which are small, and microscopes are pretty much an illumination source, something to hold a specimen, an optic to adjust the illumination, and an optic to magnify the image, and then some way of recording the image. And that hasn't changed from Robert Hooke's day until now. So I'm going to organize my talk along those lines, and I'm going to talk about the electron microscope's illumination, the optics, the specimen, and the camera in succession. First, the illumination. Why do we use electrons for looking at things which are much smaller than what Robert Hooke was looking at? Well, they're waves. In 1925, Louis de Broglie proposed that electrons were actually waves. And within a very short time, a theory was developed that you could use a magnetic lens to focus electrons, and Ernst Ruska and Max Knoll developed an electron microscope. You can see that the wavelength of an electron in the range used for electron microscopy is quite a bit smaller, about 160,000 times smaller than that of light waves, visible light waves. So that held out quite a lot of promise. Now there are a few bumps along the way, a few challenges, and I'll get into those. Another reason that electrons are good is that you can make a very coherent source. And coherence means something slightly different in electron microscopy from what it means in lasers. In lasers, you're dealing with photons, which are bosons. If you have an excited atom and a photon goes by and excites another one, it will excite it into the exact same state, and it can do that indefinitely. You can have millions of photons in the same quantum state. Those are all coherent. Each individual photon is coherent with the others. In an electron microscope, you can't do that. There's no stimulated emission of electrons because electrons are fermions. However, you can make the source as point-like as possible, and you can make it as monochromatic as possible. And what that gives you is it gives you electron waves, which are very consistent from one electron to the next. The pattern and shape of the wave as it travels through the microscope and through the specimen will be as consistent one with another as possible. And what that means is that then the whole collection of electrons that accumulate when you detect will be consistent with each other, and you'll have a visible or a detectable interference pattern that you can analyze. Another reason that electrons are very good for looking at specimens, especially like the specimens in cryo-electron microscopy, is that they interact much more strongly than any of the other probes that have been considered. X-rays are photons with much higher energy. They have a much lower cross section for interacting with the specimen of microscopic proportions than electrons do, and as do neutrons, which have an even lower interaction cross section than X-rays. This was shown by Richard Henderson, who's one of the winners of the Nobel Prize for development of cryo-EM in 2017, in a quarterly review of biophysics article in 1995. That same article, I should say also that because of the higher interaction cross section, it also means that they're more likely to be detected by the detector. X-rays are very difficult to deal with across the board. And I did spend a little bit of time trying to build an X-ray detector myself, and it is they are difficult to detect because they tend to go right through a detector. The other most important piece of information in that 1995 Quarterly Review of Biophysics article is that the amount of damage done by the X-rays per amount of information delivered is very high compared with electrons. Basically, X-rays, when in sufficient quantity that they do interact, deposit a lot more energy into the specimen and do a lot more damage. So now I'm going to talk about the optics just a little bit. And again, this is not a lecture on microscopes per se, but just relating microscopes to the important aspects which help with cryo-EM. So at higher KVs, like what we use, at 50 and above KV, we prefer to use magnetic lenses because they exert a force on electrons which is proportional to the velocity. So they don't get weaker and weaker or they don't have a lesser and lesser deflection capability as the energy goes up. There is an odd mechanism by which they work. Electrons are deflected by a fringe field, which induces a twist. They start to go around the axis of the lens like this, and it is the motion of traveling around the axis of the lens which then interacts further with the field and causes a restoring force which brings them into the center. This has been shown by Otto Scherzer to mean that they can only be converging, and there's a theorem called now the Scherzer theorem that you can't correct spherical aberration with an arrangement of round lenses alone the way you can in light microscopy. So there's this divide in electron microscopy between microscopes which have aberration correctors and which don't, because the aberration correctors are much more complicated, involving multiple lenses, and were only developed in the at the very beginning of the 2000s. I mean, they've been worked on for decades at that point, but the success came when the aberration correctors could be controlled by computers and have ultra-stable electronics. So they were some time in coming. But my point here is that by maximizing the gradient of the field, the rise and fall of the field in the pole piece, by having the pole piece be as narrow as possible, and by limiting ourselves to a very small aperture angles, resolutions better than 2 angstroms can be achieved by electron lenses, which means that the electron optics is not the limiting factor for most of cryo-EM. That may not be true indefinitely, but for now that's the case, and there's a huge amount that can be done in cryo-electron microscopy with non-aberration corrected microscopes. And in fact, if when aberration corrected microscopes are used, there are other issues that arise because for now in electron microscopy, the spherical aberration is actually one of the principal mechanisms for generating contrast. And I'll get to that. So just looking at the Abbe criterion, the typical aperture angle of 10 milliradians gives you about 1.25 angstroms resolution. And in practice, it's a little bit worse than that. And you can see that in an electron microscope, you get lattice fringes in a polycrystalline gold layer at the 2.3 angstrom spacing of the 002 lattice line and the 2.3 angstrom spacing. The 2 is very vague. I don't know if you can see it, but it is there. So again, just a little bit more discussion of the electron microscope as compared with the Hooke's microscope that I showed. We want parallel illumination here because we're going to be doing averaging of particle images. And so we want the illumination to be as consistent as possible across the field of view. We're not going to use an objective aperture because we're going to want to do phase contrast, and the objective aperture is used for removing high angle scatter out of the beam to make amplitude contrast. So we don't need that, and the projector system. I just wanted to make the comment that because of that twist that I told you about, the images are in general rotated by magnetic lenses, and you can arrange the projector lenses to compensate for that so that you can independently control magnification and rotation. That's especially important in tomography, where you would like to have your detector aligned a certain way with the tilt axis. So the specimen, again, if you want to look at things with angstrom level resolution, you have to hold them with angstrom level stability. So the holder is quite an issue. This is just a photo of a recent development at Catan in the last few years of a holder for Cryo-EM, which has a rotationally symmetric doer, so it can be tilted without changing the cooling characteristics of the doer. The specimen chamber is quite crowded. It's quite a design challenge to fit everything in there because you, in addition to the pole pieces, which render the field strong for getting the low spherical aberration, you also have to have a hole to let the beam through. You have to have a hole to let the tip in. You need to have an anti-contaminator, which those are blades above and below the specimen, which will capture gas, water vapor, etc., near the specimen. Colder than the specimen holder, so that it keeps the specimen holder clean. And of course, you have to clean the anti-contaminator periodically. There's also the objective aperture, which we're not going to use for phase contrast imaging, but it takes up space. And there's the fact that we want to turn the specimen holder to do tomography. So it's quite a crowded space. The microscopic aspect of specimen holding is in the grids, which have been being developed continuously over the last 10 or 20 years, with instead of randomly placed holes, there are now manufactured holes in a carbon foil And just recently, gold grids have been proposed and introduced by Chris Russo and Laurie Passmore at the Laboratory for Molecular Biology at Cambridge, at the MRC, with in collaboration with Quantifoil. The last level of holding is the vitreous ice, and of course that is the least stable element in the system. There is a certain amount of irreducible noise in the system, regardless of how stable you make the holder arrangement. So these three together, the illumination, the optics, and the specimen, then interact together. The microscope has an effective potential which steers the beam through the specimen and to the detector. And the specimen itself is a wave object to a good approximation when it's thin. Those two together create a mapping, which is like a potential interference pattern, which when the electron is ejected from the source becomes an actual interference pattern. And that is what is detected by the camera. But it's important to note that before detection by the camera, the image has noise already. It has the shot noise of the beam. So it's the role of the camera to not do any harm to that, to not increase the amount of noise that's already there, and to not reduce any resolution that's already there. So that's the goal of the camera. So there are a number of challenges to that. The first one is multiple scatter of the electrons. Again, the advantage of the electron that it interacts strongly means that it's definitely going to generate energy that can be detected in the detector, but it also means that it's going to have this scatter effect, which is going to have both the effect of increasing the noise and the effect of reducing the resolution. And it's going to reduce the resolution in a noisy way, so it cannot simply be deconvoluted. In addition, and this wasn't clear initially, the electrons generate energy that's going to be detected stochastically along the track. The energy that's generated by the electron, as it loses energy to the detector, is exactly the same energy that is studied in an electron energy loss detector. And there are many mechanisms that take energy from the beam. Many modes of energy conversion, which have different characteristic energies. So you have a kind of shot noise of energy, but with variable size shot. And this noise is called Landau noise. And it creates a rather wide distribution of possible energy deposition when you have a beam hitting a detector. A third issue is that the size of the beam interaction volume is very energy dependent. And if you want to push the energy up high to 300 kV, you have to accept the fact that the interaction volume of the electron in the detector is going to be quite large, and you're going to want to mitigate that in some way. At low kV, the interaction volume is significantly smaller, which suggests the possibility of slowing the electrons down before you detect them. And I'll touch on that one more time in a few slides. But by and large, that's not how that turns out not to be the best way to do it. So for a while, when I first joined Gatan, which is now a part of Amatec, a astronomy grade CCDs were a new thing, and it was a big thing to build an electron microscope camera out of it. And a number of ways of doing this had been tried already with a lens, in particular by Jim Powley, with a 1,000,000-volt microscope. He had tried a lens-coupled arrangement. But fiber optics, fused fiber optic plates have this nice property that they accept light at very high angle and then use total internal reflection to channel the light vertically. So we coupled scintillators to our detectors, to the astronomy grade CCDs with a fiber optic, and that gave a very sensitive output, which was very useful for a lot of things. But it had this problem that even though the detection layer was the scintillator and was very, very thin, the scatter that happened in the fiber optic plate below was still just as large as it was in the simulations I showed you earlier. So, so these cameras were not able to generate the kind of signal quality that was needed for cryo-EM. The cameras were online, which made it possible to start developing automated tomography systems. But the use of film continued for some time after the development of CCD cameras, because film actually had some nice properties, it turned out. One is that it was a transmission medium, so the electrons exit the back face of the film before they do too much scattering. In addition, the substrate is plastic, which is less scattering, so there's less coming back. The scatter is more is lower in angle. And a third thing that was not appreciated early on is that grains in film are kind of an all or nothing phenomenon. When they develop, they either develop all the way or they don't develop at all, which makes them kind of like a counter, and that had the effect of reducing this energy deposition noise. So to understand these phenomena, or we needed a metric to describe this, and just looking at the noise in the image wasn't adequate because of the blurring of the signal. The blurring of the signal tended to make the noise look less than it was. We needed a way to look at the signal to noise ratio in a fair way. So the other thing is that the signals were not just missed or detected like they are in a light detector. What happens in an electron detector is that some electrons generate a lot of signal and some generate a very small signal, and that creates noise, even though all the electrons are generating some. It's basically a pulse height distribution. So the metric for this, and the way to address the blurring issue is to go into Fourier space. If you Fourier transform the image, you now have a virtual detector of frequency channels, and the frequency channels don't alias one to another as long as the system is linear, so that the rules of Fourier transform apply. You now have channels each of which can be assigned a signal and a noise. So in frequency space, this new metric was called detective quantum efficiency and is defined as the signal to noise ratio in frequency space that comes out divided by the signal to noise ratio in. And actually, it was discovered. This was not named DQE at first, but it was discovered that the whole the whole theory of this was already well in use in medical imaging, and so we followed that lead. It was originally called signal to noise transfer efficiency, or STE for short, and was published in Microscopy and Microanalysis somewhere around 1994 or something like that. In any case, so how do you go about addressing this scatter? One way is to just go with it and say, well, we're going to have the entire point spread function happen in the scintillator, and we're going to use a reducing fiber optic to reduce the image onto a sensor. And it turns out that doesn't work very well because the reducing fiber optics have a lot of light leak, and it's enough that it basically cancels the benefit of using the larger pixel. I mentioned deceleration earlier. That was tried, and one biological study was done with it successfully, but it was deemed impractical as a development for commercialization because it would require a decelerator in the camera chamber of the microscope, which doesn't have as good of a vacuum as the beam source. So what we settled on was a transmission arrangement, and we attempted to build a transmission scintillator camera. S here is the scintillator. This is a beryllium mirror to minimize backscatter, and a very large numerical aperture camera, shown here, about 800 millimeters long, almost a meter. This is mounted at the back of a GIF at UCSF behind a Polara, and a back illuminated astronomy grade CCD. So this was a very difficult project. What it yielded was interesting. It was disappointing, but it was interesting because basically we did everything right. We got rid of the scatter, and yet the DQE was still only modestly better than a fiber optic camera, which is the blue curve. The green curve, it just shows what happens with the lens, which is a much weaker detector of light than a scintillator camera. But that's not so interesting. With what happened with the red curve, we came to understand through simulations was this energy deposition noise, which had not been included in our simulations up until then, generated this variation in the pulse height spectrum, which was the noise that dropped the DQE. So in a fiber, you're collecting a much larger fraction of the track. In a transmission scintillator camera, you're only sampling a very small fraction of the track. So you don't have as many of these energy loss events, which means you have more noise in the energy loss events. So right about that time, we started talking with Peter Dennis at Lawrence Berkeley Labs, who had been working on a active pixel sensor, a silicon active pixel sensor, which was thinned, and which by virtue of it being an electronic detector with no intermediary, the indirect cameras are called indirect because they don't directly couple the energy of the electron into the detector. They turn it into light and then send it through a fiber and then turn it back into an electrical signal. In the case of a silicon APS, the energy generated by the beam can be directly collected and thereby have significantly higher signal to noise. What this allows is discrimination, and I'm going to zip through this. discrimination is basically a matrix of four possibilities. You have, on one axis, you have what happened, whether the electron hit or not, and the other is what we thought happened. And this is what you want. You want to think it happened when it actually happens, and you want to think it didn't happen when it didn't happen. Those are both good things. And if it did happen and you miss it, that's bad. And if it didn't happen and you detect it, that's bad. So that's discrimination, and you call this ratio of true positives to all of the actual electron hits sensitivity, and you call true negatives to all of the no electron hits selectivity. And so this picture of actual electron events in a detector shows you why this is challenging and a bit daunting. An event that looks like this is no problem. That's probably an electron, and you detect it as such, and you're probably going to do pretty well. In this noise region here, you can reject that, but you have to reject it. You have a lot more of those pixels, so you have to reject them correctly a lot more times. This little blip here might be an electron. And in fact, some of the weak electrons are some of the highest resolution ones. So you'd like to get those if you can. But if you lower your threshold to get those, then you might get a flood of false detection. So you have to be careful. And then you have events which might be scatter. And they're, when you have two hits close to each other, is it one electron or two? You have that issue. So another way of looking at this is with the pulse height spectrum. So here's what read noise would look like, and here's what the electron hits might look like. The actual image histogram that you see is the merge of these, and you don't actually know what these tails look like. If you pick, what you want is to pick the level as threshold, which equalizes the number of false detections from noise, and or call that background, and the number that you miss of actual events. In addition, when you are discriminating, you have this possibility of looking at the signal around the pixel and deciding what part of the pixel the electron landed at. And it turned out this technique worked really well. Here are some events with black dots placed in the quarter pixel of what was deemed the centroid. And this shows an image of, again, gold lattice. In fact, this is the same image I used for the previous slide. In linear, this is at a low magnification, so that the gold lattice, the 2.3 angstrom gold lattice fringe is above the Nyquist frequency of the detector, and it shows severe aliasing. It shows that the pixels have very high resolution natively, and that they are oversampling, or that they are undersampling the signal. So one nice thing that super resolution does for you is it gets rid of this aliasing of all of the signal and also all of the noise in this region, and that improves your DQE. So now we're going to look at the DQE of this new system, this counting, centroiding, transmission, direct APS detector. This shows the progression from the detector alone. This is still linear mode, not counted, but transmission. This is counted, and then this is super resolution. So all of this, whatever is out here, gets aliased down into this band when you don't do super resolution on a undersampling pixel. So this shows the benefit of doing the calculation to get that extra information. Interestingly, film comes in kind of close to the thinned APS uh, without counting, and the fiber optic coupling is way down here, and this huge jump from this level and the level of film, which was doing most of the cryo-EM imaging up until that point, this huge jump up to here is what caused the resolution revolution. So when you boost the signal to noise ratio, one benefit turned out to be that you could fractionate the image without vastly increasing the read noise. If you try to do this with a linear detector, you're taking an exposure that had one read noise at the end of it, and you're changing it to an exposure that might have had 20 or 40 read noises added to it. With counting, the read noise is basically discriminated away. So you can do this much more effectively. So these images this is from a figure in Lee et al. 2013, which is now an often cited paper that that Yifan worked on. This shows the motion that was measured in this movie. You can see that the resolution in a simple sum of the movie is confined to one orientation, and the motion measured is pretty much unidirectional. It's not always that way. It can be very curly, it can be very still, and give you a good image without motion correction. However, with motion correction, now you have tone rings all the way around. And this changed the experience of people trying to do cryo-EM from finding, only occasional really good images to having nearly 100% hit on good images. Um, and this yielded a significant improvement in the resolution of a proteasome at the time. So the point I'm making is that you get an improvement in the image quality from the direct detection, but then it also enables another helper technique of motion correction, which then makes the image quality even better. That's a kind of leveraging effect. Another leveraging effect is that the CTF determination is better. Your image quality being better means you can determine the CTF better, and then what that means is that if your CTF is critical, because if it's wrong, you're going to flip the phases of the wrong frequency and make the image worse. So a way of looking at this is that better DQE gives you better specimen images, which give you better processing in a kind of direct way. But it's more than that, because it also allows you to operate at lower defocus, which then feeds back into your better images. It also allows you to do better drift correction, which gives you better images. And the better drift correction also further increases your ability to lower the defocus. And it makes your CTF measurement better. Also, because processing is often iterative, even a small increment in DQE is going to be potentiated by this iterative process. And then altogether, that gives you access to higher resolution or smaller molecules, whichever, and both happened. In addition, because it's long been known since the 90s that you needed to do energy filtering to do tomography with thicker specimens. You can combine a good imager with a good spectrometer to do zero loss filtering, and that gives you a further improvement. This is a this is a very strong effect in a 300 nanometer tomography specimen. It's a weaker effect, but it's still a meaningful effect in just plain cryo-EM imaging. The specimen ice can often be 100 nanometers thick. So there is a signal to noise ratio benefit. So, and this shows that that our efforts to overcome this noise problem, and our goal originally was to be better than film. It turned out our cameras were significantly better than film. It created this explosion in the number of molecules that had their structures determined. Down here at the bottom, you can see that the K3 bioquantum, that was the earlier name for the GIF, or upwards of 1,200 structures in 2023, and I don't have the current number. And of the just the plain K3 without the bioquantum, upwards of 1,700. But that's the well-known story. So there have been some newer developments, and I'm going to talk about a number of things and actually venture into a little bit of material science, because it turns out that these cameras, because they're fast and sensitive, can also be quite useful in other areas than just cryo-EM. But I'd like to talk about the two new cameras, the Alpine Vista and the Alpine, which were designed specifically for cryo-EM at low kV. So these cameras are just two different size variants of the same thing. It's a special detector, which is much more sensitive to 100 kV electrons, or it's much more, it gives much higher resolution with 100 kV electrons than the K3 does. In this graph, you can see the dark blue is the K3 and the light blue is the Alpine at 100 kV. And the Alpine Vista has the same DQE curve, just more pixels. And this is just comparing with other manufacturers' cameras. The CETA is a fiber optically coupled camera, and fiber optically coupled cameras do better at 100 kV than they do at 300 kV. So the reason for this camera is being a little bit more credible is that it is at 100 kV, but the direct detection still wins out. This shows that it still has pretty good performance at 200 kV, and so it's really quite a useful camera. It's not recommended for 300 kV, but and these are just some structures that were gotten by the Alpine. So the smaller area of the Alpine was intended to make a more affordable camera, and it's a very important point that more affordable camera is capable of doing some pretty impressive things, getting very high resolution at 120 kV and 200 kV below 2 angstroms because of its high DQE. So the main difference between the Alpine and the Alpine Vista is that the Alpine Vista can take a larger field of view, so it can acquire more particles and converge, roughly 3 times faster. It's roughly 3 times the area. Um, and again, you will notice that the look and feel of these slides changed now, and because these are slides that I borrowed from our marketing department that has much more skilled graphics people at their disposal. But this just shows the argument that if you have a better camera in your screening microscope, it can change your workflow for the better by a lot. So here's what happens if you have a problem with your freezing conditions or your uh, your preparation. You have to go back and redo something. Uh, Sometimes you have to screen at the target kV as well. So all of this takes time. If, however, you have a better camera earlier on, you can get this full circle screening done at the same time that you're doing your initial screening, and it improves your efficiency in your workflow significantly. And then you can skip this part because you don't need to go on to a 300 kV microscope. So now I'm leaving Cryo-EM. I'm going to talk about using these same cameras uh, for materials applications. You can see that the image quality comparing a fiber optically coupled camera with the K3, which is configured here to take it's using the same capability of K3 to fractionate the dose, but it's using it to make movies instead of to do motion correction and resumming of the image. You can see the extreme improvement in quality over the over the fiber optically coupled camera. And you can use the same time resolution to study sudden onset crystallization, for instance, coupled with experiment monitoring. Um, the Metro is a camera which uses the same detector as the Alpine Vista, or a very similar detector, the same technology, the same technology which gives it good sensitivity at low kV. Um, and so 2D materials are very beam sensitive, and this gives you the ability to look at those with much less criticality of the beam, the dose. So, and again, this is just a very small sampling of these because I don't want to, this is a cryo-EM school, but it's just, this is so closely adjacent that I wanted to show you. The 300 kV version is optimized for 300 instead of for low kV. Same idea though. And then this is a something we have in the works. Basically, it's a fundamental improvement in the detector signal to noise ratio and speed. This is what the electron events look like at a certain contrast level on a technology very similar to the K3. And this is the same events. These are 300 kV electron events. I'm sorry, 30 kV electrons. And the reason we're using 30 kV electrons is they give a fairly uniform pulse height distribution around 30 kV. And these events have the same number of electrons in them, but these are much more spread than these. And that means that the resolution of this detector will be higher. This is just a small test sensor. The resolution of a sensor based on these pixels will have higher resolution and much better detection signal to noise ratio because the peaks will be higher. So we're looking forward to what we can accomplish when we build this technology into a camera. And that's it. I'm afraid I didn't quite.
Actually,
I'm sorry.
No.
Paul, thank you for such a great talk. So I have one question. So I think you showed the DQE for the K2 camera with the super resolution. It's quite good. I'm just wondering if we do the real space binning of the super resolution image, then how does the DQE will be changed?
So I'm going to go back to that slide because that slide already answers your question. This is basically what it does. Roughly speaking, it's the ratio of the sync function for this size pixel to the sync function for this size pixel squared, roughly speaking, because the noise power spectrum is roughly constant at high spatial frequency. So most of the change in the DQE comes from the MTF change, and the MTF change is different because of the sampling aperture, the change in sampling aperture. Does that make sense?
Yes, it does. So the counting mode means binning of the super resolution image by a factor of 2, so the DQE decrease. Then if we use the free space binning, so the DQE shouldn't be changed, right? Just be truncated.
I'm sorry, can you ask that the second question again?
So let's say we take an image with a super resolution mode, then we do the binning in free space instead of binning in real space or hardware binning. So then the DQE shouldn't be changed.
Correct. That's correct. Yeah. In fact, that's recommended.
Okay. So then have you any idea just how much effect this will be on the structure if we use the hardware binning?
So that's a very difficult question to answer. And I can point you to a paper that came out from UCSF 2 or 3 years ago, which compared it compared well, okay, it's hard to say. Actually, that paper was CDS versus non-CDS, which was that's another very interesting study because our cameras have the capability of doing CDS, which reduces the noise. But most of that benefit is here at high spatial frequency. And if you don't do super resolution, you don't see as much of that benefit. So a lot of people are not using CDS when they really should be. And with that paper from UCSF does some actual reconstructions and looks at the rate of convergence to high resolution. So it's a very quantitative study, which shows that there is a benefit to CDS. And even though CDS slows the camera down by a factor of 2, because of the improved DQE, the convergence is still faster. Net, the convergence is still faster. So and what I can't remember clearly is whether that paper also compared super resolution with counting. And I apologize, but I can get you the reference to that paper if you're interested.
Yes, please. Thank you.
Are there any other questions? So I'm sorry I didn't go the full hour and a half that was requested. Uh,
No,
I
it's
think
okay.
the
normally-
hour and a half was also meant for some discussion.
yes.
If I understand it. And because
figured-
if people have a question about my talk, and I'm also happy to.
Yes, absolutely.
What Li
Absolutely.
said was a mixed together for the question and answer together.
That makes a lot of sense. That makes a lot of sense.
Yeah. Thank you. Thank you for your talk.
My pleasure.
If anybody has any questions, feel free to just, I think at this point we just unmute and ask the question, or you could write it in the chat and I'll read the question out loud.
Hi, Paul. Very informative talk. So I have a question. What's the limit of the current current electron camera?
Limit in terms of what? In terms of resolution? In terms
Yeah,
of
in terms of resolution.
so so that's a very hard question. So the thing about resolution is that, I mean, you have a very complex instrument which has a lot of things going on, and you have very complex specimens which have a lot of things going on, and you have a very complex specimen preparation methodology as well. So there are a lot of factors which contribute to what ends up being the resolution. And there's also the fact that the specimen is composed of long chains of amino acids which are folded and are cross-linked, sometimes weakly, sometimes strongly, and so you can have a molecule which is very rigid, like apoferritin, and that sort of regularly provides high resolution to everybody who tries it. And then you can have other molecules which are very floppy, which are extremely challenging. Now I'm not a biologist. I can't remember the name of the molecule, but there was a structural study done by Yigong Shi at Tsinghua University on Ifan, you can probably help me out with this. It was on the cover of Science magazine, the molecule.
I think it's a spliceosome.
Yes, it's the spliceosome. That is it. Yes. That required a lot of games to be played where parts of the molecule were masked and what are they called? Ifan, what is it? What are the sums of 2D images which are classified into a particular angle? What are those sums called? Those images.
2D class average, or I don't know. I don't
Yeah,
know.
2D class averages. Yeah. So
Yeah.
so the molecule was approached by masking parts of it and just doing cryo-EM on parts of the molecule one at a time and then assembling it. And those kinds of techniques are continuing to be developed and becoming more and more sophisticated so that the conformational heterogeneity of proteins can be dealt with. So just like you can use the signal in your image to do motion correction before you ever do any cryo-EM processing on the molecules that you find, you can use grosser parts of the structure to create a kind of template or framework to do analysis of the details of the image. It's kind of like a bootstrapping of a succession of priors. And so again, because there's so much involved, there's the heterogeneity of the composition, there's the heterogeneity of the conformation, the floppiness of the arms of these molecular machines. There's the camera. There is the fact that when you put the specimen into water with a little bit of detergent to try to keep it from sticking together, it's still a lot of the protein still goes and sticks onto the air-water interface. There are all these different things. So it's a nearly impossible question to answer. What is the limit? And I personally would say there is no limit. And I would also say that a lot of people say it no longer matters how good the camera is. You can do this with any camera because the specimen is the limiting factor. The specimen is the true bottleneck. I personally don't believe that. And the reason I don't believe it is because the specimen isn't the bottleneck, it's the challenge. And if you can use these techniques to look at if you can do cryo-EM on a smaller subcomponent of the molecule and bootstrap your way to the whole molecule, again, you're not creating a three-dimensional rigid image of the molecule. You're creating a model for what that protein is and does. So if the protein has flexibility, ultimately, the 3D model that you're going to create has to embody that flexibility. And if you have that flexibility, again, it's just any statistician will tell you that if you want to study more variables in a situation, social scientists wrangle with this the most. The more variables you want to study, the more data you need and the better data you need. So I think that the role for the camera is important going forward. And we're very excited to be developing a camera which is going to have better DQE, even though people are telling us that DQE doesn't matter anymore.
Thank you. Thank you so much.
Mm-hmm.
Ligo, did you want to address the question in the chat?
Maybe you can ask.
So the question in the chat from Annalise Holland is: we collect our gain reference in super resolution mode, and we bin to a factor of 2. So I was curious what you meant by binning to 1 was okay and in fact recommended.
Okay, so if you bin by 2, you are going from super resolution to physical pixel resolution. And when I say bin by 1, I mean physical pixel resolution. I might have mixed my terms in a confusing way. Does that answer the question?
Annalise, does that answer the question, or do you want to clarify further?
I think that answers the question. I'm sorry, I'm so new to this, I'm not even sure. So for now, thank you so much.
So actually, I had a question for the audience if anyone wants to chime in. I was kind of guessing as to what to put into this talk and what to leave out. I wasn't quite sure. And I am not as much of a microscopy expert as I am a camera expert. But the material that I put in about the microscope, was it helpful to this audience? Feel free to say no.
I think it was very helpful. I think we have a very wide range from beginners to experts. So I think what you covered was great.
Thank you.
And everyone in the chat agrees.
Great, great.
Enthusiastic.
While we are waiting for questions, so Ivana, I'd like your opinion and experience on the pixel size to image. I think let's say in old days with the 60 camera, so the achievable resolution is 3 times the pixel size, just 2/3 of the Nyquist frequency. But now with the direct electron detector camera, the theoretical limit is just the Nyquist frequency. So that means, okay, if I want 2 angstrom resolution, then I can just take an image at 1 angstrom per pixel, or should we go to 1/3 of that targeted resolution, like in old days for the 60 camera, just say 0.67 angstrom per pixel? In your lab, so what's the practice you usually do?
Interesting question, but at UCSF, we basically standardized the data collection for all users, unless someone has a special needs. Say I have a certain reason I want to go to whatever, right? So we typically, I think, getting the physical pixel is about 0.5 angstrom, around that range. I don't remember exactly. And then the microscope is always set in the exactly same magnification. And then the user comes in, they're basically collecting, they choose, like say, what the focus range they pick. And then the rest of them, they basically don't change much, and if at all. The reason I think is that this avoiding a lot of, because for majority of people, majority of user, all they care much is about getting the structure. And then in terms of just simple about seeing getting the structure, the other related question to you is, your question is also, to me, is always like I say, at what resolution do you really need, what question do you need to address at what resolution? For example, if you're not looking at it, like I say, small, like a molecule binding, drug binding, you want to look at all the side channel, everything, specifically like how it binds these small molecules, things like that. For most sample, like a 2 to 2.5 angstrom, or even 3.5 angstrom, is sufficient to address your question. Getting higher resolution simply making you feel happier. And in terms of the information you're attracting there, is not really much. And then the other thing I think to me is nowadays that we're putting more emphasis on the throughput, because our tests show that by the end of the day, the more image you get, you always end up better off. Right? So like, for example, in our place that we normally don't collect in super resolution. We typically just collect, even this is not a recommend, even from time to time. Then the reason is that if you collect super resolution, you're basically lost about 30% of the throughput or even more, about that. And then given that 30% or more particles, you probably can make up with the EQE loss and all the other things. And then the question also is that what is really limiting your resolution? As what I was talked about it, is like, to me, that unless your sample is really engineered, very stable, or has very defined discrete states, most time the resolution was limited by the sample, by the flexibility, by dynamic behavior. And then if you get a much larger data set, you have much better power to do the sorting and stuff like that, then you are better off. So back to your original question, what is the resolution? Unless someone specifically have a specific reason and has also believed that their sample, for example, they really want to see water molecule, how they arrange it on sample. And then they know that their protein is very stable, can get to that level of resolution. They may want using higher magnification, smaller pixel. But other than that, so why bother? So that's kind of our approach. It's not very particular, but in terms of from the facility angle, it's very efficient. Therefore, everybody getting within certain amount of time, you know that if you sample the eye thickness is good enough, product distribution is good enough, you will get enough micrograph.
Okay, thank you. So just now I missed the setting. So at the UCSF, what pixel size do you usually use?
I think it's about like a half angstrom physical pixel size.
Oh, half angstrom. That's quite high, right?
Yeah, it's about 0.4 something probably, right? 0.4 angstrom. Then your Nyquist is about like a 0.8, and I don't remember if it's a physical, but most people collecting them in the, say for example, if you're 0.4 angstrom physical pixel size, then your Nyquist, and then you're collecting this not in the super resolution, and but with the if you're collecting physical pixel size 0.4, that's not, then you're basically your Nyquist is 0.8 angstrom to 0.9 angstrom. That's sufficient for most sample, which getting about 2 angstrom resolution.
Okay, thank you.
So we have a question in the chat, and then we will stop there and take a short break. So the question is, what would be the preferred setup for quote unquote hard projects that would absolutely prioritize resolution and quality if that exists? For example, for structures that are hard to align and prone to converge to false minimal.
If this question to me, I would think that for this kind of, so what would be the preferred setup for hard projects? I would absolutely as resolution over quality. So I still think in majority of the case, if your resolution is say limited to say 3 angstrom, or it's because that the protein is probably stable and then alignable at that resolution level. And simply by going to higher magnification, most likely won't help. And but rather than using other tricks, for example, for the alignment is often dominated by lower resolution, particularly harder to align. The so-called hard to align particle is probably more like a featureless one. And in those, you probably want to go to higher defocus, and then rather than higher magnification. And I don't think there is a specific sort of setup, right? Yeah.